Good. Practice makes perfect. So let's give it the old college try here. Here we go. Where were we? So it says an mitomalani synthesis was performed using each of the following alkyl halides. Now, the alkyl halide is what I call the electrophile, right? In each case, draw and name the amino acid that you make. So let's start out by drawing our diethyl acetaminophthalate. So we'll start with that. And it's kind of a rehash in a way of what we just did in the last problem, but whatever. It's still good practice. So now we're going to take this in the first step, sodium ethoxide. In the second step, we're going to use methyl chloride. So we have methyl chloride, and so we're going to add a methyl group. Let's throw that methyl group in there, like this. So we have our methyl group, and then we have our amide here, and then we blow the whole thing apart with aqueous acid. We just heat that in acid, and that will do its thing. And everything that's going to be part of our amino acid will be all of this part right here. So you can see that we end up with alanine, right? We end up with our carboxyl group. We have a protonated amine down here, and we have a methyl group over here. So we end up with alanine, and it is racemic. So we can take the same rationale for this one here, the one that says isopropyl chloride. Isopropyl chloride, it's this portion, right? If you have methyl chloride, it's this that ends up as the R group. So if you have an isopropyl as your R group, what you're going to end up with in that case is a valine. So we end up with valine for this one, valine. And then for the next one, you have 2-methyl-1-chloropropane. So you have 1, 2, 3. And then you've got 2 methyl. So you've got an isobutyl group. So if we draw what the product would be then, we have our carboxyl group. We have our nitrogen. And then we have an isobutyl group. So methylene followed by 2 carbons like this. And that is a leucine. So we end up with leucine in this case. And there's my positive charge. And everything is racemic. So I'll put here, this synthesis is racemic. We always end up with a mixture, a racemic mixture, this synthesis. All right. Everybody, give me a thumbs up if you follow me on that one. Just a lot of repetition in there, but you know, repeating things is the best way to learn. You know, organic chemistry. Okay, cool. Let's take a look at 25.17. Now we're on to the Strecker synthesis. This is the one that you made the alpha aminonitrile, right? So it says identify the reagents necessary to make each of the following using the Strecker synthesis. So this is the one where you start with an aldehyde. And the first thing we want to make is methionine. Let me draw the structure of methionine for you. It's kind of an interesting structure. So methionine looks like this. You have CH2, CH2. Then you have a sulfide at the end, a methyl sulfide. So if we want to make this compound, the part of it that's going to come from the aldehyde will be all of this. Okay, that's the part that comes from the aldehyde. And so our aldehyde is going to have 1, 2, 3 carbons, then the sulfur, then the methyl group. Right, I'm just counting like this: 1, 2, 3, then a sulfur, and then we have a methyl group over here. I'm just counting out loud so I don't mess it up. So we draw the starting aldehyde. So it's got 1, 2, 3. Then we have, so am I counting right here? Yeah, I am. But I'm drawing it a different way than it is there. So let me draw it. I can leave it the way it was. So we have 1, 2, 3. And then we have our sulfur, and then we have our methyl. There we go. So that's enough carbon. So that's our aldehyde. The Strecker synthesis, the first step is to treat the molecule with ammonium chloride. Again, this is a mechanism that is found in our textbook. I don't ask my students to know it. They've learned enough mechanisms at this point. So now we have this carbon is going to be attacked by the cyanide, and you're also going to have the amine attached to this same carbon. So let's draw what that will look like. We're going to have something that looks like this. So here's my two carbons. There's my sulfur. There's my methyl. You're going to have the nitrile, and then you're also going to have the amine on it like that. And to make the carboxyl group, all we do is we take it and we heat it with some aqueous acid. So you can clearly see all the carbons. Look, we've got 1, 2, 3, 4, and then the sulfur. Look, 1, 2, 3, 4, and then the sulfur. So it's the nitrile is kind of the key, right? You take that nitrile and you heat it in acid, and you end up making a carboxyl group. Right, that's something that we saw in the the carboxylic acids chapter. Let's see here. For histidine, let's see, why don't we, that's a lot of practice here. We could try histidine quickly. So histidine looks like this. We have a carboxyl group. We have an amino group here. It's protonated. And we have that ring that I told you about, which is called an imidazole. So it's kind of an interesting ring. It's aromatic. So it looks like this. Anyhow, so histidine, the portion that's going to have to come from the aldehyde would be all of this. And so our aldehyde is going to be something that looks like this. We're going to have 1, 2, and then we're going to have our aldehyde like that. Again, first step is to treat it with ammonium chloride and sodium cyanide. That's going to give us this. So I'm just going to kind of flip it around here a little bit so it's easier to digest maybe. We end up with this, then we have a methylene, then we have our ring. There we go. So it looks like this. And there we go, something like that. And then after hydrolysis, with aqueous acid, we end up with histidine. And again, we end up with a racemic mixture no matter what. I'm looking at my notes and I have an exclamation points at the bottom. All are racemic. Everything that you make is racemic here. Let's take a look at a couple more, then we'll call it a day. It says, each of the following aldehydes was converted into an alpha aminonitrile followed by hydrolysis to make an amino acid. So this is the Strecker synthesis, just like the last one. So Strecker synthesis. Okay. Draw and name the amino acid that was produced. Let's start with acetaldehyde, just a 2-carbon aldehyde. It's the second simplest aldehyde there is after formaldehyde. So we're going to treat that with ammonium chloride and sodium cyanide. We're going to end up with the alpha aminonitrile. So we have the nitrile here. We have the amino here. Then we're going to cook that in some acid. And we're going to hydrolyze that to a carboxylic acid like this. And then we have this. Now, I've drawn it a little bit differently, but this is the same thing as if you were to draw this. It's identical. And so that is alanine. So we end up with alanine. And again, it's racemic. Let's try another one. If you had 3-methylbutanol, 1, 2, 3, 4, 3-methylbutanol, the exact same approach, ammonium chloride and sodium cyanide. We get the alpha aminonitrile, which looks like this. We have the nitrile, we have the amino group, and then we hydrolyze the nitrile and acid. And of course, we protonate the amine, end up with this. Oops, it's not very pretty. There we go, where we have the protonated form of the amine because we're in acid, and we still have our proton, and we hydrolyze the carboxyl group. If you go into the list of amino acids, you'll see that this is leucine. And again, everything in here is racemic. So we'll put racemic. All right, we'll skip the next one because I got so many examples in here. Why don't we call this the last question for the day? It says, identify the starting alkene necessary to make each of the following amino acids in an asymmetric catalytic hydrogenation. So this is the expectation for the asymmetric catalytic hydrogenation, and I got my expectations from Dr. Klein, author of the textbook. So let's say you want to make L-alanine. If it's the L isomer, that means the amino group is going to be pointing out like this, okay? So I like to draw them in this orientation. So what that means is that your starting material is going to have a double bond here, and that's where you do the asymmetric hydrogenation on. So you have your NH, and it's protected as an acetal. The first thing you do is you hit it with hydrogen and the chiral catalyst with that ruthenium and everything, and that adds the hydrogen to the back face of the molecule. So you've got a hydrogen in back, and then you have your amide out here. So to hydrolyze that amide, first you put it in base, and that hydrolyzes it, but that gives you the unprotonated form of everything. So to protonate it, you put it back in acid. So this is the expectation of a chiral catalyst. All I expect you to do is to know the conditions, and that here's where the double bond would be, and it's always going to add so that you end up with the L isomer. So this is L-alanine. All right. So for valine, it would be the same thing. You have your isopropyl group in valine, right? Valine is this, okay, NH3 plus. Okay, that's what we're going to end up with. So what we do is we convert this into an amide like that, and then we put our double bond here, and you do the exact same thing as before, and you end up with L-valine. All right, so I think what we'll do is we'll save this one, leucine, and maybe we'll come back and we'll do this one as well, the next class. And when we start lecture on Wednesday, we're going to begin by looking at the structure of peptides. Then we'll get through the structure of peptides, which isn't a very long section. And then after that, we get into, well, I guess it's a little bit. Then we get into how people determine the structure of a peptide. I mean, it's got so many amino acids. How do they know which is which? You know, how do they figure out how they're all linked together? So we talk about a couple of ways that that's done. One thing is the Edmond degradation. Then we talk about enzymatic cleavage. There's a pretty neat problem. It's right here. If you want to go ahead and take a look at it before class, it's neat. I wouldn't call it a brain teaser, but it's kind of interesting trying to put it all together. You feel like a detective trying to figure out this problem. Then we get into peptide synthesis, a huge area of organic chemistry. Making peptide bonds is big money. There's lots of ways to make peptide bonds. I'll show you a few. And then once we do that, we'll look at peptide synthesis in more detail. We'll look at protecting groups. And once we get through that, we look at the Merrifield synthesis. And I think that's the last synthesis that we look at is this thing here, which is a solid phase synthesis. So if you're wondering, how do you do chemistry on something that's solid? Well, I'll explain to you what that means. And the whole thing about protein structure, that would be more of an FYI, especially for my students who are taking biochemistry in the fall. I'll let you do that on your own if you want to go over it. I might review just a little bit of it. And I'm sure it's a review for some people who've taken biology already. And then the whole thing about protein function, we're also going to skip that. But you notice that there's no summary slide at the end of this. I think there could be something in the book where he covers everything. But so that's all we're really going to cover is 3 more sections. And we'll be finished with the entire chapter on Wednesday. And then we'll spend the rest of the class doing some practice. I have some really cool practice problems like that peptide sequencing one. This one here. Again, I encourage you to give this one a shot on your own if you want. And if not, that's okay too. But yeah, that's a lot of organic chemistry in a day.